It's 2:05. Looks like we have a decent showing, so I think it's probably a good time to start. So today we're going to be talking about Anthropic's second interpretability paper called In Context Learning and Induction Heads. They spoke about induction heads in their last paper on this kind of stuff, and I'll walk through that as well. But yeah, let's go ahead and get through it. So just starting with some of the key concepts. So what is in context learning? And the basic phenomenon that they describe it is that, as they describe it, is that with large language models, it's really common that tokens later in a given context are easier to predict than earlier. So you can think of that in lots of different contexts for why that might be the case, but that's the basic thing that at least they're going to try to study in these next several slides, whatever. So that could mean a couple different things. There are lots of phenomena that could fit that description. Um, and they operationalize in a specific way. So one way you might think of this is just by basic statistical or knowledge associations. So if you just happen to know the capital of Azerbaijan, then that's something um, that's just more like what a language model is trained to do in general. So that may or may not be exactly what they mean by this. In fact, they kind of more liken it to another couple concepts that are pretty popular, like few shot learning, where you can, since language models are very good at manipulating the context to do a particular kind of task, you can also kind of train them to do different tasks within the context by giving them a couple examples. That's a really popular and impressive feature of large language models these days. And you can also engineer it to do different things just by kind of tweaking the prompt in ways that might suggest certain things. So um, that's particularly useful in things like clip guided type of image generation, or I'm sure we've all seen cases where you can just have the most aligned AI ever do something, and it would be much more suitable for that. I think that was part of what their lab assistant paper also talked about. Um, they're not going to take a super crucial stance on which kinds of things they're talking about in this paper. And instead, they're going to operationalize the concept in terms of decreasing loss and increasing token indices. That's a bit more dry, but a lot more precise. So effectively, what that means is just that, again, that um, on average, language models are much better at predicting things later in the context than earlier. They're also going to make a score out of this to analyze in lots of different contexts. So they're going to take they often work with contexts of length 512, so 512 tokens, and they're going to take I think it's 10,000, something like that, 10,000 contexts, and run language models of each of those contexts, and then they'll take the loss of the 500th token and they'll subtract off the average loss of the 50th token in context, and that should be their measure of um, in context learning by this definition on average. Um, one kind of interesting quirk about this they find, which is really weird in my mind, is that the relationship between context index and this kind of in context learning score is really regular. So on the for each line in this plot, you have different models. So you have a that span all many different ranges of parameter sizes. You go from 13 million to 13 billion, and you plot the average in context loss, I guess I'll call it, um, by the log of the context index, and you see this really clean relationship. Um, it's kind of hard to read the axes on some of these plots, but I can tell you that this is a log scale on the bottom. Um, but yeah, you see this really clean relationship, and so they'll make a score that's based off of this later, or that they will operationalize the kind of slope of this nice relationship here. Um, but this is also to motivate the fact that the score as they've operationalized it here with these 500th and 50th tokens isn't necessarily sensitive to the specific indices you choose. You get this really nice, smooth relationship between the loss scores as you move forward in the context. Okay. So then what are induction heads? Um, a kind of rough way to understand it that I like to use is just that it's an attention head that attends to the token that followed the last use of the current one and then copies the, the, the following token. So here's this one kind of schematic diagram they use in the paper. So if we're looking at the node token, what the induction head is going to do is going to look at the last time node was used, attend to the token right after that, and then induce or increase the likelihood that the model will produce that same token to follow the last instance of this token. So you can also represent it kind of as these kind of nice symbol forms where you have a pattern A goes to B and you later encounter A, then the induction head will encourage you to produce B after A the second time. They also make that definition a bit more precise. They say that an induction head is one that performs both prefix matching and copying, um, and they'll introduce scores for that to make that also more precise as we go on.
Precisely the last time, or does it also look at even more previous times?
You can look at more than one time. Yeah, that's one of the reasons why I put tildes around this, because it's not necessarily just the last time. It could be um, multiple different times. It could be a couple times ago. It could be some version of this. I should note that the way they make a prefix matching score to quantify this characteristic is based off of the last time a token shows up, I believe. So I think we'll get to that later, but I just wanted to flag that issue for now. Okay. The paper as a whole is framed in 6 arguments for a particular claim that induction heads are responsible for a majority of in-context learning in large language models, or I guess in transformer models in general. The arguments that they're going to give are not thought to be knockout arguments. It's not as if you should walk away from this paper fully confident that that's the case. But they're trying to build an evidential case, and they want to build a norm of reporting results even if they're not fully conclusive, because they expect that to be the case for lots of things going forward that are still interesting. I'm going to try to cover some of the qualifications they give in the paper and alternative hypotheses, but I'm probably not the best substitute for just reading the paper. There's a lot there. The arguments are pretty sophisticated, so I would encourage you to read the paper if you haven't yet. They also analyze a bunch of different types of models. Similar to the last paper, they analyze attention-only transformers, which get rid of MLPs and a couple other pieces. But they also analyze models with MLPs as well as really large transformers as well. I'm going to cover as many of those as I thought I could in a reasonable amount of time, but there's some results I'm going to skip. Okay, so argument 1, that induction heads underlie a good portion of in-context learning is that transformer language models undergo a phase change during training. This is something that's actually been seen in a couple different contexts before, but they're claiming to explain a particular kind of bump in the training curve that I'll describe in a bit. But during that phase change, induction heads form, and simultaneously in-context learning improves dramatically. So this is a kind of observation that something happens during training, and in-context learning improves right at about the time that you detect induction heads occurring within the network. They give you these nice little handy tables as well for each of their arguments where they try to give kind of ratings of how well their arguments apply at different regimes. So on the horizontal axis, you have attention-only models, models with MLPs that are also small, and much larger models. And then there's an argument that induction heads contributes some of in-context learning and contributes the majority. Across all of these, I think this particular argument, well, I think and they think that this is just kind of correlational evidence. So it's good to keep in mind. But what exactly is the finding? So they take that in-context learning score that I mentioned before, and they apply it throughout training. And in this plot, they're doing that for three attention only models. One has one layer, one has two layer, one has three layer. The one layer model does shows some trajectory, but the two and three layer models have this big dip in context learning score. So that means that the in context learning improves a whole bunch in a relatively short amount of training time. So that's interesting. That's particularly interesting because the mechanism that they proposed for induction heads before requires at least two layers in order to work. And we'll reference back to this a couple times going forward. This is also the case for the networks with MLPs. So this is kind of extending the results to what they had before to networks with MLPs. And it's seemingly also the case for these really big models. The data here is interesting. You'll see that the relationships are much more coarse because they only have, I think, 15 time points in training where they made these measurements, I'm guessing. But or I think they mentioned having 15 time points. I'm not sure if they only evaluated those at those time points or exactly what happened, but the data that they show is about 15 time points throughout training, and you still see a similar dip at about this time. To motivate to again kind of motivate that their choice of the in-context learning score isn't driving something like this, they took the relationship that I showed you before with this thing, that the loss improves as you get further into the context, and they made it a graded version of the score, which relates the derivative of the loss with respect to the log token index. So that should give you a version of the slope of this line that pops up here. And what you see is that in the one layer attention only model, you see some kind of blur that doesn't have many qualitative shifts in it. The argument is that in the two layer and three layer models, around the time that you see this big shift in their original score, you also see a qualitative jump or like a band in the score change. So that this is motivating that their particular choice of score wasn't, especially the indices that form the score weren't particularly important for the basic effect. They also apply, so that's nice that something happens that, okay, it's nice that something happens that changes this in context score quickly. That's already interesting. It's also interesting that this occurs only in models where they think that induction heads can form, but they haven't really associated this with induction heads specifically yet. So what they're going to do in addition is develop a prefix matching score. So this is based off of their notion before what induction heads do. So again, they're going to look at, this is using their user interface from the last paper. So what I did is I highlighted on this token 1396. This is a stream of random tokens repeated 5 times. And so I clicked on this one to highlight that it should tell me when I'm at this token, what other tokens am I attending to in order to figure out what to do next. And when highlighting 1396 in this slot here, I'm attending to 5012, which follows the last iteration of 1396. So the idea is that this prefix matching score should quantify the fact that I'm attending to the thing right after the last version of the last use of this token. Right. Okay. So in order to form this score, they're going to take 4 steps. The first is to generate a sequence of 25 random tokens. It's kind of similar to what they had before. They're going to get rid of a couple tokens that are, I guess, troublesome to work with. I guess just to get rid of statistical regularities that pop up. They're going to repeat the sequence 4 times, and they're going to compute the attention patterns on top of this. The prefix matching score is the average of all attention pattern entries attending from a given token back to the tokens that preceded the same token in earlier repeats. So It's the amount. It's the average of the scores that looked at this that preceded um, this token. I don't know if that makes sense.
Another way to check this, and what I expected you to talk about here, is that they could hard code a model that can only learn attention heads, and then they could see, like, they could draw a scatter plot of whether the model starts doing well on the same training examples that an induction head hard coded model would work well on, right?
They will do a version of that for the next argument. So they're going to
Nice.
make it easier to learn induction heads, and they're going to show that in context learning improves a lot, even faster than the standard version. So that's pretty related to what you said, but not exactly the same. Okay. But when they make this prefix matching score to try to explicitly look for induction heads, they see that indeed these heads just kind of appear within this window. So throughout training, the one layer models have nothing like this. The two layer models suddenly sprout a bunch of attention heads that look a lot like this, that attend to the prefix or that match the prefix. And the three layer does as well. This is a particular point that's actually pretty interesting because if you look at the um, networks with the MLPs, um, you see a similar kind of result, but it also looks a bit more complicated. So you do indeed always see that these heads tend to develop around this band that corresponds to where the in context learning score improves. But you also see some other stuff that's pretty interesting. So you see these other lines in this three layer with MLPs models that kind of slowly build over time. I should note that the color of the lines for each of these heads correspond to how where it's positioned in the model, which layer it's positioned in. The blue, the deepest blues are the later ones, and the redder ones are earlier in the model. And even with the two-layer network with MLPs, you see that there are some heads that seem like they might develop into heads that show prefix matching, but their their prefix matching decreases over time. So it's this story seems super interesting and it does fit the general description of what they say, but it also seems like there's a lot more going on here. That's also especially true of the much larger models. So they also run this prefix matching score with a bunch of other attention heads. And once you get to the highest networks, there's just all kinds of stuff going on. There are lines that come up and down. There are lines that take forever to develop, and so on.
Can you say more about how the evaluation about a layer is done? This sounds so far like it would be done to the entire model at once.
It is. So, well, okay. I shouldn't say it is in general. I think for the smallest models, they do this for every head. For the larger models, they take a random sample of heads. I believe it's 100 or something like that.
How do you take a sample of heads? The heads are just like implicit, right? You can't take them out.
Uh, I'm not sure. Yes, you can. I mean, you just take the. I mean, yeah, you would. You just take the attention scores across the different heads. Those should be separable. You're not taking them out of
Oh,
the
you mean
loop.
you identify particular heads, parts of the model as attention ones, as attention heads, and then look at them while like just ablating out the rest of the model?
No, no, no. There's no ablation happening yet here. This is just observing what happens during training.
Okay, so this is the score that it would have if you used only that head.
Okay, so let's look at the prefix matching score is just trying to is a quantification of what behavior they think this head has about its attention. So like where they're trying to quantify a characteristic about its attention pattern. So you can think that, let's say an attention head only attends to the previous token no matter where it is in the sequence. You can come up with some quantifying score to say, no matter where it is, it's going to attend to the token right before me, or it's going to attend to the token two before me, or something like that. This is just a version of that. It's just a descriptive quantification of what the attention patterns look like. It has nothing to do with changing the function of the model while it's training or anything like that. or running inference. Does that make sense? So this is just saying, I know that, well, okay, my hypothesis is that induction heads are going to look back to these particular cases where things repeat. So if I take the average of those scores that look like they're looking for things that repeat, does it show up? They're just trying to come up with, so yeah, you can imagine that you could, in their last paper, they did a lot of manual work to basically identify these patterns, but you'd want something quantifiable so that you can run it in an automated way and pick out heads and things like that.
Oh, so this is something that works on the attention model in particular, because that one just like works directly with numbers attached to particular indices.
Yes, I believe that's right.
Okay, thank you. Then I think I see the confusion now.
Okay,
The confusion was with what was actually written on the y-axis here.
got it. Yes, so this is just the score of a particular head at a particular point in training. The score meaning how well it matches prefixes. Okay. Um, right. But again, this has lots of different cool, details packed within these plots. Okay.
Right, so the early layers always pay attention to the last time that this showed up, but the late layers do other kinds of processing.
I think it's, well, okay, for the smaller models, it seems like that's the opposite actually. It seems like the
Oh, right,
later
yeah, I
layers
mixed up the
have,
colors.
yeah,
Shit.
the later layers have more induction heads than the earlier ones, which I think at least partially makes sense because you need a composition. Well, okay, at least by the mechanism that they proposed, you need a composition of heads in order to do this. So you need at least two layers deep in order to even do this at all. So you would expect that overall there'd be at least some delay in this for the smallest networks, and then later all kinds of stuff happens.
Sorry for saying so much, but I expected that other people also confused.
No, no, this is good. I'm really glad you're asking these questions. It's helping me to understand what I'm not explaining clearly too. Okay. Are there any other questions at this point? Okay. Right. So it's cool that you can run these scores and see kind of qualitative jumps in how the model performs, but you can also even see this particular jump on the overall learning score or on the overall loss during training. So here's just the loss curves of these models throughout training. And they've superimposed the one layer score on top of these. And you can see that there's a bump in the training curve that corresponds to this time period where um, both by their metrics, induction heads develop and in context learning score improves. So this bump that happens in the learning score or that in the loss um, corresponds to some kind of qualitative jump in what the model's doing.
Does the two-layer model have twice as many parameters as the one-layer model?
Oh, that's a good question. I don't think so. I don't think it's twice, but I think it's probably close to that. I don't think these are controlling for the number of parameters, but I could be wrong on that. I haven't
The
looked.
obvious question is whether you can take a 10-layer model and flatten it out and to two layers and get the same curve.
Well, yeah, hmm. I believe the answer to that is no, but they can also do the reverse of that, which I think goes to the next argument again. I think you will like the second argument, and it should answer some of the questions. But I don't think they've flattened out. Yeah, that's a good question. If someone could look at that up, that would be great, but I don't know off the top of my head like how the parameters counts for these look like. I think in general that's not the case because at least they also analyze these, which are clearly not controlled for parameters. Um, I believe they've also experimented with several versions of these, so it would be weird if just increasing the parameters would do this. But I think they can give you some evidence that one layer shouldn't be able to do this at all. Okay. Um, right. So this is talking about the loss curve. You can look at the same kind of analysis with the MLP layers. And sometimes you see a bump, sometimes it's kind of harder to see. So this seemed like a point that was a little, that also has some hidden detail in it. And with the larger models, it's particularly difficult because again, you don't have too many time points to look at to try to figure out what's really going on. Um, so kind of hard to say there. Another thing they look at along the co-occurrence lens is by looking at um, the vectors of loss per token. So if I have a context, I just made it words because whatever. So you have a string of words, and you have the amount of loss on each word in each cell here. So that's each one of these is one loss vector. Um, you can evaluate this over many different uh, prompts, and you can do this at different points in training. So that's what the vertical axis here is depicting. So you have the loss of this sentence over lots of different points in training, and you can analyze these in lots of different ways. They did this with, again, 10,000 examples, each 512 tokens in length, and these are randomly selected in training. So there's 10,000 examples per vector, and then there are a bunch of samples throughout training as they could sample, I guess, in most of these cases. If you perform PCA of those vectors, you can get an idea of how the how the loss changes through in terms of the tokens over time. So if it's the case that similar tokens are learned or are the network learns how to handle similar classes of tokens, you'll see you'll see components of this space relate to one another. And so they summarize the learning trajectory of these models using PCA across those loss vectors I mentioned before. If you do that, you see that the shape of these trajectories, so training goes this way, um, has a pretty similar shape. So you start from here, you move in one direction. These are the first two components of that PCA space. But when the induction heads and in context learning score window happens, you see this yellow shift happen. That's a big curve in how this PCA space looks at that exact same time. And it only happens for models that have two or more layers. This is actually surprisingly consistent across um, the models, the attention-only models, the models with MLPs, and the larger transformers. You basically always see this shape that it comes through one direction, takes a big turn, and then kind of levels off.
So the interpretation here is that induction heads have no reason not to follow, not to form right at the start, except that the particular pieces of data that it would work well on are handled relatively fine enough by the initial model, but the initial training phase makes the model do worse and worse on those training steps until induction heads are incentivized enough to appear?
That could be a good interpretation. I don't think they're even going that far. I think all they're saying is that there's this qualitative shift in what happens that corresponds to this window, so it must be important for the model. But I think, yeah, I think you're going even a step further. I think that's really interesting. If you look at the points around this shift and look at how the loss changes for different tokens, you see interesting patterns that correspond to what they think induction heads are doing. So if they look at the loss of B minus A, so there's this loss vector for all the tokens at B, a loss vector for all the tokens at A, and they just take the difference between those. The red in this text above is where the model better predicts tokens, and the blue is where the model does worse in predicting the tokens. And the pattern is that If if the context is repeating what happened before, similar to what you think an induction head would help you with, then the model performs better. Whereas if it counters what an induction head would tell you to do, the model does worse. So in this case, if you go to uh, Mrs. D. Ersley, so at this token, um, the previous versions of this were again Mrs. Dursley and Mr. Dursley. Um, but when it reaches a new name for Mrs. Potter, the model does worse here because it thinks it's going to fall up because the induction heads by this argument are pushing it to um, produce Dursley as well for this name. And whenever there's a Dursley, the model does better. Um, the Potter seems to be better because that seems to be repeated a few times. Repotted. That's funny. I think there's something else, but yeah. Does that part make sense?
Yeah, what happens when you look at more than 2 dimensions in
Good
the
question.
PCA?
They don't show it. That is a good question. Yeah. Okay, well, they don't show anything more than 2 dimensions. I should say that it is interesting to me, at least, that the first 2 dimensions seem to always look like this and have this big swing. So these are the dimensions that should explain the most variance. So that's pretty significant.
Yeah, this is great. You should do the same thing with other models than transformers, and then see whether this keeps happening and is therefore more like a statement about the training set rather than the
Oh
architecture.
yeah, that's a really good point. I like that idea too.
In fact, maybe we can promote or prevent the formation of attention heads by fine-tuning on the parts of the training set that this PCA indicates.
Hmm. Yeah, it's these model. Well, I think it's pretty standard practice, but these models also never saw new training data. So it would be interesting if regularity in the training data would give you more signal like this or not, or if there are particular examples that would make this learn faster or something like that, or make the model learn this faster. Anyway, okay. Um, but in sum, the basic argument for argument one is that there's this big shift in the model where a bunch of stuff happens at the same time. So in context learning score improves, um, induction heads seem to form, and the loss changes kind of significantly. Um, at least there is a visual change in the loss. Um, there are lots of things. So maybe there is something that developed in the model that encourages both of these things at the same time. So maybe induction heads aren't the thing that completely underlies the in context learning score improvement at that point in time. Maybe it's something else that develops at the same time, but um, at least they seem to go hand in hand at this point. So argument two is more active. So what they're going to do is they're going to change the basic transformer architecture in a way that, well, just to read, they change the transformer architecture in a way that shifts when induction heads form or whether they can form, and the dramatic improvement in context learning shifts in a precisely matching way. So what they're going to do is use their proposed recipe from induction heads from the last paper. The last paper says that one way to implement induction heads is to use one attention head to move information from the previous token to the current token. So you move some information from node to struction, um, and once that is done, you use a second attention head to query the information moved to struction that matches a similar kind of information from node. So then you take the second attention pattern to basically fetch the stuff that was moved into the right slot by the last attention head. Um, this is based off of a key composition, so they think this works through the key terms of the self-attention mechanism. So I think the manipulation here is that if they allow attention heads to directly see the key of the previous token, you can achieve both of these steps in one layer even though you couldn't do that with one layer before. You would need at least two. You'd need one attention head to you'd need to do this in series with multiple attention heads. So they're going to introduce a new parameter to learn in the model, where for each attention head you have you derive keys the normal way. So you have a key for layer, I guess this is for layer J and head H. But then you modify the key for layer J and head H by blending it with the key from the last token in the sequence. And so this is a trainable parameter that determines how much you want to blend these two together. And this is just the sigmoid function. So this is just giving you the exact form of how these two are blended together. So the final key that's actually used for the self-attention mechanism is a blend between the original key, the normally generated key, and the key from the last token. This isn't a recursive formula. They just apply this once you've generated these keys. Does that make basic sense? Well, suffice it to say that I think that all they're trying to do is make it easier for attention heads to learn um, this specific mechanism of induction heads that they proposed in the last paper.
Where in the architecture is this step inserted?
At all of the self-attention mechanisms. So whenever you generate keys for your query key lookups, you would do this.
Okay, so first it calculates the keys as normal, and then it calculates this formula for the like from the keys as normal.
Yeah.
So that it looks like a saw blade pattern, perhaps.
Could you
The
what was
dependency
that
graph.
last term?
Saw blade pattern. In
Oh,
other
okay.
words,
Yeah.
in other words, the two appearances of kj are actually two different variables.
That's correct. That's what I'm trying to indicate by not recursive. This is just from the form that they use, but this is before the transformation, this is after the transformation.
And what you would have done was put a hat on the left side, on the left cape.
That's right. That's right. Okay. On the top row here is the same in context learning score plots from before. And on the bottom is when they introduce this change into the model. They call these smeared keys models. And you can see that all of a sudden the one layer models are able to have better in context learning scores than before. And the two layer models are also able to learn or to have improve their in context learning scores faster than before. So this is a simpler you don't need to learn the two layer composition of heads. You just need to learn, that you need to learn that one parameter instead of a whole attention head that feeds into this mechanism. So the hypothesis is that should make this faster, and it does seem to make it faster. They claim that this is medium in interventional evidence for small attention only and small with MLP models. It's interventional because they could design an experiment to have a particular effect, and it had that particular effect. There are lots of other things that could, well, they don't do this directly for large models, but I think just from, I don't know what they base this part of the argument on. I forgot that part of the paper. Does anyone else remember? Okay. Well, suffice it to say, again, that's another flag to read the paper for exactly how they qualify these things, but that's argument 2. Okay, so argument 3 is that they're going to try to basically knock out induction heads in the model that they detect using their metrics, and they're going to see if the in-context learning worsens when they perform these knockouts. So here's a diagram of what they're doing from using one of the diagrams with the last paper. So here's just a schematic of the transformer architecture. Um, you have the self-attention mechanism here, the MLP layers. You have embedding and unembedding. What they're going to do is they're going to take one of the heads that they think, well, an individual head at a time that they think is an induction head, and zero out its contribution to this backbone residual stream here. However, they're not just going to propagate the model forward after that. They're going to, before they knock out this head, they're going to run the model unaffected in order to determine what the attention patterns are going to look like from this point on. And then they're going to zero out this contribution to the network and then propagate forward, freezing the attention patterns to what they were in the unaffected version of the network. The idea is that if they just outright zeroed this attention head, that would have all kinds of cascading effects in terms of which tokens look at which other tokens, or the general functioning of all the attention heads. They think that that's probably a more severe ablation than they probably intend. So I think that's how this works.
Did they just zero this out like in the analysis afterward, or did they actually do it in the network and then run it?
Yeah, so they did it in the network and ran it. Again, freezing those attention patterns, but they propagated the that forward after this was zeroed out. Does that answer your question?
Yeah, it does. I'm just kind of thinking, wow, that's really cool. They can freeze the later part and know how to make those kinds of modifications. But I'm
Mm-hmm.
curious how they did that. But that's cool.
Cool. Okay. Right. So these are the same. This is just showing the same windows from before to give you a context for where these things happen. On the top row, on the bottom row, each line is an attention head. They color the lines according to what they think the head is doing, based off of other metrics that they talk about. They have the purple lines they think are induction heads. The pink lines are previous token heads, and the yellows are just unmatched for either of these. And you can see that when you hit this window, a lot of purple lines develop, um, the pink lines develop, and when you knock out these purple heads, the in context learning score gets worse. It's also interesting to note that when you knock out the previous token attention heads, the ones that just attend to the token before the current one, the in context learning score improves, quote unquote. I think they talk about this in the paper a bit. They mentioned that this happens because it just makes the model a bit worse at predicting overall. So if you're also predicting the earlier tokens worse than before, then that gives you more like better opportunity to predict the later tokens, which would um, increase your in context learning score overall, even if you're just overall worse at predicting things. So you've got like two sides of the in context learning score: the early in the context and later in the context. Um, Knocking out the induction heads, they're going to argue. I suspect that they'd argue would make predicting the later context worse than it was before, um, and knocking out the previous token heads would make the early context predictions worse than before.
It sounds like they look at how knocking out a particular head behaves during training, but the thing that each head does changes during training, right?
That's right.
So wouldn't that make this inconsistent? Like, if you look at, I suppose that they simply identified what each head does at the end of training, but
No,
after
no, no. They're doing
20%
this
of...
throughout training, so that's why all the colors change. So that this point is where these heads change by and large, but I'm you can notice that
Oh,
the colors are changing from yellow to purple in this region where
okay,
induction
so
has developed.
since they are doing it at each point, like to every head, they can get away with um, not having to care about what it does early or late. Yeah, nice,
Yeah,
sorry.
that's right. Exactly. Okay. They also make a separate claim that at least I didn't know how to parse at the time. They said that they looked. I think they effectively just looked at more stuff, and they said, in fact, almost all the in-context learning in small attention-only models appears to come from these induction heads. I don't quite see how they got that from the data itself. Um, there might just be something I'm missing, or there's some other plots that look at how the knocking out an individual induction head relates to the shift that happens within this window. Um, and indeed, knocking out the induction head changes the loss vector in the same direction as what happens during this window. But it seems like that's the claim that um, the in-context learning, or almost all of the in-context learning, comes from the induction head seems to be based off of something like it seems like you would need to motivate that by saying that if you knock out all of the induction heads, then all of the in-context learning goes away. Maybe they're assuming that if you like knock out each individual attention head and take the sum of all of their contributions, it would add up to most of it. I don't think it's that naive, but I'm not sure what to think about that yet.
It looks here like only yellow heads can become purple, while orange heads stay orange. I imagine that in 10 years we might have like 10 more types of heads,
Oh yeah,
and
almost certainly. Yeah.
and then that does sound like eventually the model might, during training, run out of yellow heads to specialize.
Oh, that's an
So that
interesting
sounds
point.
like you want to be able to like add additional heads during training.
I mean, that's
One,
true. These are also pretty small models. We did see a whole bunch of complexity with the larger model. So when I this thing, so this is doing a version of the detection algorithm for induction heads, and you can see that these things change in and out of the score. It's definitely not a one-way transformation across the board.
okay, nice. Yeah, I can see that the purple head may become orange there.
Yeah. Oh, well, these are different colors. Sorry, these colors correspond to its position in the network. The later colors correspond to their classification of the heads. But the classification is based off of the y-axis in this plot. But the basic observation that the heads just kind of go up and down would suggest that they change their roles throughout training as well in
Maybe,
large
but now
models.
that you've said that, I hope someone ever checks whether heads ever change roles.
Yeah, yeah, me too. That's a good point. Okay. This is. I think this argument was particularly interesting, and I think that the data is like the data that is presented is kind of the roughest. So if you look at the version, they have like the main thread of the paper, and then they have this model analysis table where they break out the results for um, the models with MLPs and the bigger models. Um, you can see lots of other interesting kind of stuff happening with the MLP models, like the spread between their classified induction head and previous tokens thing gets much smaller as you get into deeper networks with MLPs. So that might relate to the fact that maybe the MLPs are starting to contribute to in-context learning or something, but it just seemed kind of interesting. And it didn't seem like it exactly matched this version because you had this nice separation between the purple heads and the pink heads um, in these cases where everything's kind of tightly put together here. It still is the case that the purple heads are generally on top, though there's kind of one weird one here that's on the bottom. I'm not sure if anyone saw that or knew what to make of it, but I figured I'd point out that the raw data here is a little more rough than the other parts.
In both arguments 2 and 3, they like introduce new kinds of models, and I would like really to see the corresponding PCA graphs. Like you
Oh,
should
they're
be
also
able to
there.
for each head. Oh, nice.
Wait, you mean the PCA graph for each head? That is confusing to me.
Like every head here basically is its own variant of the model. You take out this head, and now you can graph the loss or the score or whatever. So you can
Oh,
also,
once you've ablated the head.
Yes, so you can
Yeah,
also plot its its path through the same PCA space that you've shown in argument one.
that's true. Yeah, they don't show that. They do have the PCA plots for all of these different models that are in the model analysis table, but they don't have that. That would be a good idea.
Do they also have it for the variant in argument two with the key smashing?
Two. Yes. Here, I can just jump there.
Yeah, like you would have now convinced me to actually look at the paper.
Good. That's the main purpose of these things anyway, so that's good. Okay, so here are the attention only models, 1 to 6 layer. 1 layer, you just have the basic shift, and in 2 through 6, you have this big curve. With MLPs, you see the same exact thing, roughly.
Right, but with the key smashing.
I'm getting there. I'm getting there.
Ah, nice.
So we've got fewer points for the bigger models, but you see a similar kind of shape. These are much rougher. And then, oh, these are smeared keys. They actually don't have that for the smeared key ones. That's surprising. Okay.
I love these PCA graphs. I imagine that we can just discover the 10 next head types, like doing particle physics here, basically, by just looking at a few more dimensions and seeing,
Yeah,
finding more repeating.
that does seem really, really valuable. Yeah, that's a really good point. I also wish that they had put these up. I think I appreciated these less than you did when reading it, but you're right. That's a really good point. Okay, cool. Uh, Anything else here?
Uh, Quick question.
Yep, sure.
So on those graphs, like on the previous slide, I think.
Yep.
Why do we see like really small scale like correlated behavior? It looks like almost sinusoidal on these. Like, do we know why that happens?
Oh yeah, good question. I haven't thought about that yet.
But they don't like mention anything in the paper.
I don't think so.
Okay.
Let's see. So a curve amongst all of these. Let's see. So these are the differences between knocking out a head and the general model performance. So maybe it has something to do with just the fact that maybe, yeah. So not the effect of the entire model, especially once you add in MLPs, isn't just the sum of each of the individual heads. Um, so maybe there's just some like compensatory mechanism where even if you knock out any one of the heads, the others can compensate for it, or it's like particularly vulnerable to one head or something like that.
Yeah, this pattern is what you'd see, I think, is if the heads were like voting on a particular binary question, and
Yeah.
it was in some training datums, the vote is close, and then cutting out any head will change the result.
Yeah. But you're right. You also see it for the attention only models, which in theory should be basically a sum of those paths across all the heads. That's weird.
You're talking about like the perturbations, like the small bumps along the curves, right?
Yeah, yeah. So there's this shift. There's like a little bump here across all the different lines.
Even in these models, you have like softmaxes involved, right? And I think once you have softmaxes anywhere, you can construct voting mechanisms.
Yeah, that's probably a big part of this. Okay. I don't have a clear picture of that yet, but I think that there's some intuitive picture to go forward. Okay. Argument 4 is that despite being defined narrowly as copying random sequences, induction heads can implement surprisingly abstract types of in-context learning. So this is to say that this is actually, I don't know, circuits hasn't been around that long, but this is kind of more similar to the kind of quote what I'll call classic circuits work, where they look at examples of heads that fit the description of induction heads and see what else they can do. And there are lots of really interesting behaviors that pop up. So I showed you before that the classic induction head pattern of this is that if you have a sequence in the context that is A then B, and you later happen upon A, then the induction head will induce you to produce B after that. They're going to basically make that a little fuzzier and say that, well, okay, it doesn't need to be exactly A and B that are being matched here. It could be some version of A conceptually or some version of B conceptually, and these things still should have the same kind of ways of thinking about them. It's also good to note that though I'll be talking about different behaviors than this classic induction head version, all of the heads that they analyze also fit this pattern of exact induction head matching in some cases. So if they use random tokens, then they can extract these same exact heads by this definition of whether or not they perform prefix matching and copying by this definition. Or I guess they have metrics for prefix matching and copying, but I think you get the idea. Okay.
Do you mean that instead of looking at the previous occurrence of the same token, it might be looking at the previous occurrence of a token that has the same gender of the word associated with it?
Oh yeah, yeah. Actually, there. Uh, Let me walk through the examples, and you'll see exactly what I mean. But one example of that is translating between languages. You'll see the induction head, quote unquote, point to words that mean the same thing across different languages, roughly. So it's not, again, it's not exactly A, it's A star. But let's see, let's go to behavior one. Okay, so literal sequence copying is pretty straightforward. These plots are take a second to parse, but okay, so I'm going to focus on a particular token, so it's going to be number, and the blue is going to tell me what previous token contributed to predicting the number that I have highlighted, and then the red is going to tell me once I've reached this token in the sequence and I'm trying to attend to something, what is the model attending to out of the previous context. So in this case, I'm highlighting on number and it's attending to 4. You kind of have to combine results from across different highlights in order to make this make sense. So what I'm going to do is I'm going to highlight number and say, okay, I've reached number. I'm trying to predict what comes next. So I'm going to look at the red thing to tell me what to predict next. Okay, it's going to give me 4. Okay, so now I look at 4, and then what contributes the logits for this next token? It's going to be 4 for this 4. So that means that this head looked at this token 4 and produced 4 as the output for it. So it's doing exactly what we thought an induction head should do. It looked at the last thing that followed this token, or one of the, I don't know if it was the last version of number. It probably is. But it looked at the last version of number, looked at what followed it, and then tried to copy it. And you can see that this pattern of blue to red should just match token by token. So again, it's just doing that over and over and over again if there's a repeated sequence. This is the first behavior they mentioned. That is literal copying. That is like kind of standard induction head behavior. The second version of this is translation. So if I focus on English to French translation, it'll still have a similar blue-red pattern, but it's going to be a little blurrier to match the change in word orders between language. You'll still see that the basic thing holds up though. So if I go to temple across these, it'll still be kind of similar. I think that the German here is probably a little messier. The French is pretty clean.
So what happens when you have different languages where the grammar prescribes different word orders?
I don't know. When the grammar prescribes different word orders, there should be examples of that here, I think. I think they talk about that it does match the semantics of the word and not the word order. It shouldn't be exactly blue-red. It should be something related, but I don't see it here. I might just not be looking in the right place. Yeah. Okay, behavior 3 is really interesting. So this is a task they set up for the network that displays something like few-shot learning. So the idea is that they give it a stream of words where a stream of lines, and you have um, the model the game is to produce a certain number for a particular pair of concepts. If you have a month in an animal, you're supposed to produce a 0. If you have a month in a fruit, you produce a 1. Color in an animal, you produce a 2, and color in a fruit, you produce a 3. And so if you go here, here's an instantiation of the game. They limited the visualization to just the colons and the numbers. But the way I found to read this is that if you look at a number here, I'll click on this 3, then the thing that the previous tokens that contributed to how to predict this 3 were generally the previous 3s or something related. So we're looking at gray strawberry. The things that helped predict this token were gray grape, so those match the pattern of color and fruit. And then sometimes there are other things that sneak in. But generally, if you have a repeated word, so I think, let's see, let's look for a repeat. June's probably a good example. No, that one's not a good example. That's interesting. Okay, so for January apple, it's having March and apple is a really good match. September and apple is a really good match, and so on. Let's see if there's anything else. Oh, snake. So if the word is used from before, if you have a repeat, it helps predict this one a lot. I feel like there was a better example that I found before where it was the month or something. That's okay. I won't spend too much time on it. You can play with this, but the basic idea is that this head that matches the induction head definitions from their metrics also seems to underlie some of the predictive behavior of this few-shot learning task. Okay. Right. So that means that um, that they can find versions of induction heads that do that at least plausibly underlie some of the behaviors that we think relate to in-context learning. So again, it's just kind of picking out intuitive examples and showing that plausibly these induction heads are the ones that underlie the behaviors in question.
This is because it's in practice it doesn't do an if the previous word equals that word before, then, but instead it takes the dot product of their corresponding hidden vectors, and those that hidden vector presumably corresponds contains numbers corresponding to the properties of that word, such as language and kind of word and so on, and then therefore it can just ask how similar are these words.
Yeah, that's right. It's doing like a fuzzier version of similarity than exact matching. That's right. Okay.
And how does it end up that then you basically get these word rectangles, such as like man, woman, Mann, Frau? I don't know what it translates to in French.
You mean like in embedding vectors or something? I don't know.
Like, you know that you can, with word2vec, you can go from man and woman and king to queen by taking plus and minuses.
Right.
And it sounds like induction heads are doing something very similar here,
That's
right?
right. That's exactly right. I think that's the right mental image to have.
But they aren't doing exactly that, right? What exactly are they doing instead?
I don't think they mechanistically have an account for these particular heads, if that's what you mean.
Okay.
All they're able to do is show that the heads are attending to where they would be if they were doing these behaviors, and like adding logic contributions in the right places.
And if they had an exact mechanistic understanding, they could cut out the attention heads and replace them with a hard-coded version of that attention head and see
For
whether it
example,
works.
yeah, exactly. Yeah, that's exactly right. And they would also have a much stronger claim about, the fact that these were doing the right things, or that these were underlying in context learning in general. Any other questions there? Okay. Right. Argument 5. For small models, they can explain mechanistically how induction heads work and can show that they contribute to in-context learning. Furthermore, the actual mechanism of operation suggests natural ways in which it could be repurposed to perform more general in-context learning. That's a bit of a mouthful from the paper, but I'm going to take the liberty of paraphrasing it by saying that you can think of really easy ways to generalize the mechanism that they came up with for induction heads. So it doesn't seem hard that the model would learn other ways to use a really similar mechanism. So again, what they're going to do is have one attention head move some data from the previous token to the current token, and then they're going to have the second token look up some matching information from the shifted spot to see if it matches the current word. But just like Gerkengloss mentioned before, what if the previous token head isn't necessarily a previous token head? What if it shifts to other places in the stream? Then you would have a really similar effect that does a more sophisticated behavior. And if the second step of matching based off of the current token, if that took on any other form than exactly matching the current token, then it would also have more sophisticated behavior. So they think this mechanism could be easily generalized to lots of different things. And so it's pretty likely that the model probably finds ways to use it, given that it's found this first version of doing that to begin with.
This argument sounds like it's going in the wrong direction causally. Like in evolution, in biology, you can sometimes say that this animal does this thing because that would be useful for reproduction, but the architecture can't look ahead like that, right? You train it and then maybe it works, but if it works, then you can't say that it early in training adopted this mechanism because that would then later let it generalize. Maybe you can say something like that for their 10 different architectures that were tried and this one worked. Why is it the one that ended up working? Are they saying that?
I think they're saying that if you can, let's see if I can think of a good analogy. If you're learning how to walk upright on 2 feet, you can probably learn how to stand on 1 foot for a few moments at a time. Like the things are so related that you'd think that some capacity in one direction would imbue you with the capacity in the other direction. Like you have to be able to stand on 1 foot for at least briefly in order to walk on 2 feet.
I agree that that induction heads are plausibly easily generalized, but why is this an argument for their paper?
This is an argument that, yeah, that's a good point. I think they're just saying that. I think this is another version of plausibility, even if they're calling it kind of mechanistic in this case. But yeah, I don't think they know for sure. Like I said, none of these arguments are supposed to be knockouts, but I think they're just saying it's pretty plausible that this mechanism could be generalized. I think that's it.
Is it like if this mechanism could not possibly be generalized, then we would just be confused because the model couldn't possibly be working this way, and we don't see that. Therefore, this is like a necessary argument rather than a sufficient one.
I think it's
they tried to shoot themselves in the foot by looking at this and missed.
I think it's neither sufficient nor necessary for what they're trying to say. It's just that, well, I guess maybe it's necessary. It's necessary that the mechanism needs to be generalizable in order for it to underlie most of in-context learning. And it is indeed probably generalizable. But I think that's as far as they take it.
Does it need to be though?
I think
Can't it just do 80% and then the rest is done by something else in any case?
I think it would be surprising to me at least if literal copying would underlie all the stuff we see with language models. or even most of it.
What I mean is also, like, it doesn't need to be, even in this 80%, 20% scenario, it would still be responsible for most of the inter-context learning, right?
Yeah, if the literal copying did that, then yes, but I don't think that that is a fair percentage for what surprises us about in-context learning and language models.
Do you think that it does the, like, more than mere copying even early on, right after the appearance, right after the, like, yellow region in the loss history? Right after the sudden jump where the introduction has introduced?
Could you?
Because the loss doesn't change much afterwards.
Yeah, so that is where the in-context learning changes on average, and it's very flat after that. One thing they say is that the loss still clearly improves beyond that point, and a lot of learning occurs in that point. It's actually just um, you could think of it as harder in context learning still improves beyond that point because if you're trying to improve upon better predictions, it's going to be harder. So you're getting better at predicting the early context, and you need to work harder to predict the later context. I think that I think the claim is that that just keeps pace with the early context learning. But they are circumspect about whether or not that phase shift is all of in context learning in some sense. You could still imagine a case where there's a lot of learning that happens outside of that phase shift that corresponds to keeping up with the early context learning. Okay. Okay. So the last argument is just reasoning by analogy. This one's pretty short, actually. It's just that um, they looked at a lot of metrics related to induction heads in context learning on average, and the kind of loss trajectory stuff we've looked at, and they all look strikingly similar to their eyes across all kinds of different models. So it'd be really surprising if the dynamics were fundamentally different between small models and large models. It's at least the simplest hypothesis that the same mechanism is accounting um, for in-context learning in both cases, though not necessarily the only one. Not a knockout argument, just that it's reasonable to suspect that that's the case. That's basically what I just said. So lots of these metrics look similar. The mechanism being the same as simplest is the simplest explanation. Uh, yeah, all of them have the same sharp increase in context learning, same rough amounts before and after the transition. All of them trace similar paths in PCA space. All of them form induction heads. Maybe other mechanisms or forms of composition formed during the phase change is one qualification we have. Here's their summary of that table for the argument that induction heads underlie the majority of in-context learning in large language or in language models and transformer models, I should say. They think their arguments are quite strong for small and attention-only models. I think they basically nailed that down, I think. Um, for MLPs, it's a little bit tougher because they haven't really characterized MLPs that well yet, and so maybe that could contribute some to the overall proportion of in-context learning. And the argument for large models seems reasonable to them. So I guess in that sense it's medium, but there's nothing really perfectly causal or interventional to make it a knockout. There's more stuff in this paper that I haven't covered yet. There's a section on unexplained curiosities, which has a lot of really interesting pieces in it. I also recommend you look at the paper for this reason. But I think that's a decent summary of the 6 arguments. If there are any other questions, happy to take those. And then I came up with some other discussion questions. So do you think that induction heads could explain all of in-context learning? That's not the claim. But where do you think the limits might be between induction heads explaining everything and not? What would be further experiments you might do to dig into these results? I think Erkenglas has come up with quite a few at this point, but any further ones would be really good. And I think one bigger picture question I had is if induction heads underlie most of the large language model's capabilities in terms of in-context learning, what would this mean for alignment generally? But I think that's about it.
Well, the last one would sure make alignment a lot more tractable because we could replace the transformer architecture as an architecture of a pile of induction heads, and then we would know much more what's going on at any point in time.
That's certainly true. Yeah.
Yeah, good point. I guess with sorry, yeah, with the first point, I guess I feel like with as we scale to even more advanced AIs, there will be kinds of things we would consider in context learning. Just intuitively, to me, it seems like there would be, when an AI is going between like very diverse situations and with kind of multimodal interfaces and things like that, I guess I'm not sure if induction heads would account for all the kind of contextual, all the context there, but it would be interesting if they did.
So your point is just that as things get more advanced, you expect AIs to handle lots of multimodal situations, and it would be interesting if this kind of mechanism could generalize to lots of different scenarios.
Yeah, exactly.
Okay.
And I guess initially I'm a little skeptical of that. I feel like there would probably be other mechanisms involved with,
Yeah, I agree with that. Like the diagrams you showed us of the transformer models, they really show that there's a lot more going on when you get to that scale. So I think that maybe they have found a concrete mechanism for like small scale models, but I think like even the concept of learning gets generalized for transformer scale models, like the 40 layer one. A lot was going on there.
Yeah, I think I agree with that. I think there's probably more going on under the hood, but it's hard to know exactly what that is until we've done more characterization work, probably.
Shiny Demon, does your intuition there come from an intuition that something as understandable as attention heads couldn't possibly underlie intelligence, but even though perhaps something as mysterious as like advanced the algebra might?
I don't know about that, but my biggest issue with it is that it didn't seem like any heads converged to a specific level. Like, I think you said that too, that it wasn't a transformation happening for most heads. Like, there were some heads that were clearly transforming to induction heads, but most of them were like changing roles as the training went on. Yeah. So I really like the changing modes thing. I think we really need to investigate on that.
Well, these lines aren't corresponding to heads, they're corresponding to layers, and maybe some heads just get stronger within a layer,
No,
while every head still is... What? But there are 6... Wait, what? Oh, dang it. Okay. Well, scratch that. Disregard me, you win points.
There you go.
Yeah, another thing that's coming to my mind is that Rome paper discussed a few weeks ago, and where they were modifying specific knowledge in the language model up where it is, and I'm thinking of what bearing this has on it, and I was trying to look up the paper, but I couldn't find it fast enough to see, where did they locate that knowledge? Was it in an induction head, or was it some other part of the transformer model? Because that seemed like some kind of what I would think of as contextual learning.
Yeah, I bet the hypothesis would be that you shouldn't find much. Well, maybe that's not true in the generalized form, but you shouldn't find much quote unquote conceptual knowledge in one of these, I bet, because well, yeah, I guess it's just hard. At least for the literal copying heads, you shouldn't find much.
I wonder to what extent it is true that usually additional features get tacked onto the model but don't get taken out again, because instead of taking one out, usually you can just throw in another patch that handles the reason why you wanted to take it out while the thing is still useful for whatever training datum introduced it in the first place. Mm-hmm. That would sound like a lot like the hypothesis that heads specialize but don't unspecialize again. Sorry if that was non-sequitur.
I don't think I'm fully following. So where is the piece?
Like there's this
don't unspecialize.
There was like this theory mentioned today that basically heads are like cells in an organism, okay, and then cells become specialized cells, but the reverse doesn't happen. And I can imagine this happening here too, because like the incentives for a problem to get fixed by introducing a feature are there, mm-hmm, but instead of removing that feature, usually you can add a few extra lines of code.
I see. Yeah, that would make sense. I mean, maybe these lines being, non-monotonic just means that it's taking on some other role or something like that that's related, but not exactly induction heads or not exactly prefix matching the way we think about it.
Have people tried injecting fresh heads into a model during training?
I'm not aware of that, but I don't think I'm the best gauge for it.
I mean, not exactly the heads, if I can jump in, but there is work that works in the weight matrices, though. But I don't think that this is necessarily like you can trace it back to this head analysis. But many of these results are kind of, in a way, random maybe, or that it doesn't matter much. Like synthesizer is one approach that just generates random stuff and works well. So the point is that the MLP layers then do a lot of stuff. That's also the point that they make here, right? That much of it is actually happening in the feed-forward layers.
Maybe. I mean, I think they say it's suggestive that the MLPs might be doing some of the work. But I mean, at least the claim that induction heads do most of in-context learning.
Yeah,
the in-context learning. MLPs, if anything.
Yeah.
One reason I like PCA graphs is that they remove all of this confusion because they don't depend at all on the architecture.
That's true, yeah.
Mm.
I think it's interesting that in the 40-layer transformer, and as you get to a deeper architecture, the induction heads get earlier on the training, which with the scales they have, it's not that early, but since they, like, maybe it's a simplistic mechanism that smaller models resolve, right, like fall back to. And
yeah,
bigger transformers, they discover, like they have an epiphany at that breakthrough point, and then they find out that there is more complex mechanisms that they can start using. So that's probably something that like even bigger transformers or bigger training sets could show.
Yeah, it does kind of seem like the fact that the earliest layers are on the top of the 40-layer graph suggests that maybe those are just fed into other things that do more sophisticated things too. That's a good point.
I guess on a different tangent, if we're just going generally in terms of experiments to
Sure.
do, the general methodology at a high level here that's going on is that is essentially that, or at least like part of the methodology is that they look at, they come up with some strings that exhibit a pattern essentially, and then after that they, I guess they do ablations to see how the model performs. I guess with respect to that pattern, that's super vague the way I'm describing it, but
You're fine.
like you describe a string that requires you to carry out a certain computation to carry out or to be able to predict the next state of it, and then essentially what you do is that I guess you would look at the model's ability to perform that computation and what happens when you mess, if you zero out the heads like they did, or if you did other things. So I think that is a fairly general sort of strategy. So like here they're talking about they have strings specifically to look for this sort of induction pattern matching, but it's you could definitely think of maybe more complicated patterns that you could come up with,
Sure.
more complicated strings, and so one thing you could do is you could look at the capability of transformers to learn these strings, and as a function of the number of layers, right? In this case, they show you need 2 layers to learn an induction head, but you could easily think of, there might be patterns where you need at least 3 layers. There might be patterns where you need 4 layers. There might be patterns where you don't have enough layers. You just won't have enough layers.
Yes, in fact, every dimension of the PCA graph corresponds to a distribution over training datums. And like the score in that distribution of training datums is like the average loss over that distribution. And then, yes, if you look at the 10 dimensions of the PCA graph, you are going to find 10 scores. And then, as we have seen, that one of these dimensions in the PCA graph, in the 2-dimensional one, only becomes like changes a lot once you introduce the second layer. You could find similar patterns with the third and fourth layer, especially as we have seen that for the 1-layer model, you wouldn't have seen coming that introducing the second layer would make that change once you add the second dimension. You see?
I think that does at least kind of map onto what I was hearing. Is that right for you? How are you thinking about that?
Rafi, do you understand the PCA graph?
Oh, the PCA graph. I'm gonna be honest. I went to get some food.
Okay, nice.
Let's go to it. Let's go to it.
Yeah.
I think this is the most important part of the paper.
Okay. So you take the loss over a bunch of examples.
Not this one. Look at the other thing.
Yeah, but you have to understand the loss vector in order to understand the PCA. But you take the loss to a bunch of tokens in the training set, and you do this throughout training, and you run PCA on those vectors. So if they're...
Do you know what PCA is?
Yes. Yeah.
So then you see this trajectory throughout training.
And are we looking at the weights as a function of time, essentially?
No, you have these. You take a model during training. You look at 100 snapshots over time in it. You draw a table of on the 1 dimension. You have the 100 snapshots. On the other table, you have all the loss values that the model has for every training datum. So if you have 1 million training datums, maybe you include the offsets. Then you have 1 million times 100.
This is PCA in loss space.
Exactly.
Yes, you do a PCA on that 1 million times 100 table. And now you look at the 100 points that the model takes during training through that space. So we see that every model starts doing well on the same, doing the same amount of well on the same training datums, then they improve on the same training datums, apparently, up to the point at the bottom where the one-layer model stops like visibly improving, though presumably it is still doing something, whereas the 2 and 3 layer models now also become better on the same kinds of datums. So now we can, like, quite straightforwardly extract the training datums that they become better on, and we will see that they will be training datums that include a lot of repetition, for example. And then we can, for example, cut out those training datums, train only on the rest, and see attention heads not developing. And we can do this in 3 dimensions and see the next set of training datums that contain a pattern that the model will then next learn, and then that's what you are looking for, right?
Me?
Yes, you are looking for a kind of pattern that introduces a need for another kind of thing like an induction head in the model.
So I guess like what I'm describing here, like that is one way I guess you could go about looking for it. Is you could, like, the PCA is a pretty general technique, right? And they see you have one change here. So that I guess that'd be one way of doing it. But I guess what I'm trying to, or like what I was getting at, is that you can look for more, I guess, computational procedures that are happening in transformers, and you can investigate how, how, like, whether or not they're like the transformer is capable of that, by, constructing specific strings that require you to exhibit that property.
Yes, you're going the other way. You're going top down.
Does that make sense?
Yeah, sure. I'm just like the PCH thing just lets you find the natural sets that apparently the model has introduced like components for.
Yeah, it's just bottom up versus top down. So one is looking for what the model or what the model's behavior would lead you to believe are important dimensions, and the other way is saying, here are important dimensions I think a model should have. What do I need to do in order to succeed at those?
Mm-hmm. In a way, the thing they used with the like arbitrary numbers written in triangular brackets, those files sure look like they are gonna produce a very predictable kind of pattern in the model, and I can see that the stuff that falls out of that might be very like people might attack their methodology because of the kinds of training datums they produced. But if they produce their training data by looking at the PCA and extracting the set of training datums, then people basically can't argue with that, because there's like, it feels like 3 bits of complexity penalty.
It's interesting.
I guess following up on the phase change thing, then, one thing, like, I know you mentioned looking at multiple dimensions of PCA. I guess this would predict, at least theoretically, that we should see, if we looked at a three-dimensional plot, there might be a third phase change, or a second phase change, essentially, and then a third one, possibly, right?
Yeah, certainly.
Sure.
And yeah, it's essentially like you could get more, you could get more complicated, or presumably you would get more complicated behaviors as you go through these phase changes.
Yes, what we would be hoping for is that if we take 10 different architectures, some of which randomly allow a particular next component, such as because they have at least 4 layers, which is required, then draw all of those at the same time, then we would see the paths stay together for a while and then diverge. And that is what we would be able to use to deduce the existence of another kind of component.
This is actually really similar, though, to the neural tangent kernel stuff. This is exactly how the neural tangent kernel analysis worked. You would look at how the loss space develops, and you'd see this. Well, at least in theory, you'd see this really regular formation. So you should be able to even, I don't know, I guess by the kernel, you should be able to figure out what those dimensions should be.
I didn't feel that I understood the neural tangent kernel stuff like I understand this.
Well, Well, let me think. I mean,
if that's corresponding, then
yeah,
like
the fact
we need to have cover that again.
well, okay, it is. Yeah, I believe. Yeah, it should be very similar, right? Because the neural tangent kernel stuff is trying to describe how this loss vector is going to evolve over time throughout training, which is exactly what this is doing. It's just doing it without PCA. So if you could connect those two, then we'd get a lot of information out of that. But that seems easier.
Does neural tangent kernel stuff do the part where we have multiple architectures, train them both, and see that they stay together for a while and then diverge?
Yeah, not explicitly. I bet that you'd probably have to. There'd probably be some structure in the kernel that would be similar or something like that. But
yeah, but if you have to construct it, then complexity penalty. Whereas if you just say PCA and it just appears, then people can't argue.
I'm not trying to say that one methodology is better than the other. I'm just trying to draw a connection.
And by people can't argue with it, I mean they would be arguing with it with good reason. I wouldn't believe it.
I have another question / comment, but I don't want to interrupt this thread.
Go, I think we're done. Unless Nick wants to describe more about the neural tangent stuff.
I think that was a good break. I mean, I think the only observation is that the neural tangent kernel should give you good information about how that loss vector should unfold over time through training.
Okay, I'll try to look at that stuff again. Let's. But first.
Yeah. So revisiting those three kind of discussion points. The third one about if induction heads are really turn out to be really central in this, what are the implications for alignment? This will be kind of hand wavy, but I think it'll help me understand better. And thinking about how this kind of connects to famous alignment strategies or other concepts. So there's nothing in these induction heads that looks like MESA optimization to me. Right. And one thing that it does kind of remind me of is factored cognition. It's almost like there's this kind of emergent factored cognition resource where these in-context learning or these induction heads, which are kind of just a relatively simple like sequence copying thing that's very composable, has these models have figured out a way to use these to solve kind of complex language problems and things like that just by stacking them in different ways.
Well,
does that make sense?
NAND gates don't look like MESA optimizers either, and yet if you stack enough of them, you get them.
True.
Yeah, they do have, I think, a paragraph on MESA optimization in the paper where they say they don't see evidence of it, but they're not, obviously not ruling it out or anything like that for this reason. I should note that I'm kind of wincing at my own question at the bottom here. I guess I should say that they're not arguing that induction heads underlie most of the LLM's capabilities in general, just specifically. Well, okay, I think that's also an interesting discussion point, but I should just qualify that that's probably not what they're claiming.
Yeah, so I think the fact that when they do this PCA that they have this very big L at the in the two-dimensional PCA, that accounts for a lot of the shift in probability across the training curve. I think the fact that they do that, in a way, that means that this induction head behavior, at least like the change towards induction heads, is responsible for a lot of the predictive power, at least like in terms of like absolute prediction space or whatever the PCA space they use, for data that we encounter on a day-to-day basis. So for the kind of, for written language, specifically, this sort of induction head probably is doing a very large amount of heavy lifting. And I think that can tell us something about written language in general. When it comes to the world and more generally, if we're target maybe we're looking at code or something like that, although code probably has a similar behavior. One thing I might want to, if I'm just going to speculate here, is that generally I don't think humans want to try to communicate using a medium that requires much more complexity than what you have here with than what is there with an induction head, essentially, or than what can be captured with an induction head, or a couple of induction heads, or something slightly more complicated than that. So I would expect that what is required to predict human language, for the most part, or at least like a big part of human language, is fairly simple things like induction heads.
Yeah, it seems like this is the component of like just referencing stuff that you've seen in the context seems really useful. I bet there's just a bunch of extra statistical regularities that are packed into this as well, of just factual knowledge or whatever else about different things like capitals of countries or whatever. But I think you're right that being able to reference those at the right time in these flexible kind of ways does seem pretty important, and more important than I probably expected at the outset.
Yes, in a like coincidentally related manner, but like in a secretly actually very related manner, perhaps. You have that our laws of physics allow for the existence of like a few kinds of particles that are then enough to combine into everything that we know of. And the same can be said about NAND gates, I guess.
Yeah, that's right. That's a good point. That's a good analogy.
So maybe that's just a pattern that holds a lot more than it has any right to, because it's actually like it follows all the time because of like math that we haven't discovered yet, and that doesn't usually appear in like human intuition because we didn't need it in the ancestral environment.
Yeah.
I think.
Oh, sorry. Go ahead.
Okay, thanks. I think that if it turns out that induction heads are such a powerful concept that can generalize such complex spaces of information, we should see how they would turn up in multimodal contexts, because like the concept of referring to past knowledge or something else that is not at hand right now definitely turns up like in most of knowledge and most of information processing that probably our brain does. So I think, yeah, like somehow an experiment that can use something other than tokens could be formulated.
I do think that I predict that in an image you would find a similar thing for looking at a fact about a particular pixel.
I think I agree with that.
Neighborhood of that pixel.
That would be interesting to see, firsthand, but I think that I would make a similar prediction.
Do image models work like that? Do they have attention that attends to pixels rather than word tokens?
I mean, vision transformers might, because you'd have these relationships that you can query the same way. So you would have, what is the patch that preceded the patch that looks the most like this before, or something like that.
How do they do rotary embeddings if there are two position dimensions?
I bet they don't use rotary specifically, but I'm not an expert on vision transformers.
I could imagine that there's like just the obvious two-dimensional version of complex numbers.
Yeah, something like that. Okay. Well, maybe.
Yeah, this kind of strong contextual skill out of something kind of so simple and mechanistic like this surprises me. Like, I think before these large language models and stuff, I would have expected like you know, the only ways I had, maybe it was a failure of my imagination, but to be really skilled with vastly different contexts and stuff, I would have expected either you need to hand code that or you need kind of like a more general kind of agentic AI. And so the fact that you can get this with, you know, it looks like you can get a lot of this from these sort of simple, dumb mechanisms composed together is really interesting.
Yeah, GPT-2 is when I realized we could get intelligence before we understand it.
Okay, I think I should run, but I think that's probably a good point to at least officially call it. Everyone's, as always, welcome to hang out as long as possible. But yeah, thanks for coming.